Alright, so today I'm going to be talking about the Clapeyron experiment. Never have figured out how to say that yet. And giving you a little background information about it. So basically this experiment, we're going to be trying to measure the latent heat vaporization, but it can't actually be directly measured. So to back it out, we use the temperature and the pressure measurements along with a clever little formula that gives us the latent heat of vaporization. And this latent heat of vaporization is actually the amount of energy that it takes to turn a liquid into a gas during that constant temperature right before it boils. So a little background. This is a pressure versus enthalpy chart with isotherms. And you've got three regions here. You've got the liquid region, and you've got the superheated vapor region, and then you've got the under the dome region, which is that constant pressure, constant temperature region where a substance transforms from a liquid to a vapor. And since we're going to be boiling the water during this experiment, we'll be working underneath this dome in this area right here. The Clapeyron equation is that missing link that we need to turn the temperatures and pressures into the latent heat of vaporization. But in order to make this equation like really applicable to our situation, we needed to make the ideal gas law approximation, which usually is used well into the superheated region. So our apparatus, it contains a 100 milliliter flask, a hot plate to boil the water, thermocouple to measure the temperature of the water, a mechanical pressure gauge, air bleed valve, vacuum control valve, centrifugal pump, and a water reservoir, and a computer to log all the data and save it so we can analyze it. So this is what your results are going to be looking like, more or less. It's the pressure graph versus the temperature, and as you can see, it's nonlinear. So in order to get an idea what our results are going to look like, pick three different points from the steam tables and try to predict what the equation would give us for each one. So in order to do this, the first temperature I picked was 293 Kelvin, which and its corresponding saturation pressure, which is 233.9. This came from the steam table. I found the derivative, or approximated the derivative, by taking the adjacent point and subtracting it, and find the difference of the pressure and dividing by the difference in the temperature from the two adjacent points. And in doing this, I got 2150 kilojoules per kilogram, and this was substantially different from the actual value that the table gave, which was 2454. I mean, it seems to me like this would be from the ideal gas law approximation, because normally the ideal gas law is used in such superheated, and it's not usually used near the condensation point. Second point I used was 338 degrees Kelvin with the corresponding temperature of 25 kilopascals, and completing this gave me 2,145, which was also substantially off from the actual value of 2,300. However, it's a little bit closer. Third value I chose was 428, and with the corresponding saturation pressure of 543 kilopascals. But and calculating this one out actually came out to 2,093, which was very close to the 2,098. So this leads me to believe that it's possible that maybe this approximation becomes more reasonable or more accurate at higher temperatures and pressures, which would make sense because the top of the dome is the critical point, and it would it would be a gas. So there are some uncertainty that might occur during this experiment. The first is just your instrument uncertainty because of your resolution and different uncertainties embedded in the sensors. So we got the pressure gauge and the thermocouple, which are going to both have these. And then, like I said earlier, there's the systematic uncertainty, or not uncertainty, the systematic error that might occur from the ideal gas law approximation. And is there any questions?